Hi, this is our final separations project. We are Group F. So in industry, aluminum flat rolled products are typically used for packaging. And this process uses hydraulic fluid and rolling oil to improve the process and prevent equipment wear. The rolling oil is typically recycled, but can become contaminated with the hydraulic fluid as well as water from condensation. And so this highlights the need for a much more sustainable process. So our solution is to produce two product streams for the recycled hydraulic fluid as well as the rolling oil in a wastewater stream that meets Lexington's wastewater regulations. So this slide kind of highlights what is in our feed stream as well as our desired products for our two product streams and our wastewater, which we wanted to be over 0.99975 mass fraction of water to reduce our operating costs. We use the NRTL selection based on what was in our feed stream, and it's listed here.
For design methodology, we use the NRTL thermodynamic model because it accurately represents systems with partially miscibility and strong non-ideal behaviors, which aligns with the composition of our feed containing hydrocarbons, aqueous organics, and water. Our design uses several key pieces of equipment: decanter to separate water from organics, distillation columns to purify water and separate organic components, and a flash drum to separate heavier species such as dodecane and hexadecanol. Finally, mixers and splitters are then used to combine streams and set flow rates so the final products meet specifications. Equilibrium data for the butanol water and the cyclooctane water systems show that both form azeotrophs, which limits how much water can be removed by distillation and would leave the water in the organic streams. To avoid this, we place decanters at the start of the process to remove most of the water before the streams enter the distillation columns, allowing the columns to operate more effectively. For the separation of cyclooctane and butanol in our distillation columns, we use the McCabe-Thiele method to estimate the number of theoretical stages required based on vapor-liquid equilibrium data and the feed composition. This produced a reasonable starting point for the column design. From there, we iterated through several trial and error adjustments in Aspen until we reached the column specification that met our product purity requirements.
It is important to discuss other assumptions we made in our design. The main one being that our feed stream enters our first decanter at 60 degrees Celsius. We know that one hexadecanol solidifies at temperatures below 50 degrees Celsius, so that's why we made this assumption. In addition to that, we assume that our system operates at steady state conditions, all of our components are non-reactive, and water is fully immiscible in most of our organic components, except for one hexadecanol and one butanol. Here you can see our overall separation train. You can think about it by splitting it into main parts. One focuses on getting our water purified, and then our other side focuses on getting 5 streams, each representing each organic component, and then using different split fractions to get the final compositions we wanted in our products. We iterated through different designs across this whole project. We knew from the start that the distillation columns could get the job done, but we wanted to start replacing them with cheaper separation systems such as decanters and flash drums.
In addition to that, the previous design where we would just dump the waste costs about $76 million per year, and this is a quote from HWH Environmental here in Lexington. But our final design reduces that cost because it is $1.7 million a year in utilities, $3.2 million in operating costs, and a capital cost of $8 million. So in conclusion, we were able to achieve a 99.99% pure water stream for discharge requirements. Also, our return on investment was met within 1.5 months due to major waste disposal costs. The recycle stream significantly improves the cost efficiency of the system, and something that we could do to further optimize the system is edit the reflux ratios and optimize the pressures for each column. All of our columns are operating at the same reflux and pressures, so if we change them, we could possibly eliminate the need for the flash drum or some of the additional decanters that are currently being used. For the final evaluation, our process produces the recycled hydraulic fluid, the recycled rolling oil, and a clean wastewater stream. All those final compositions are shown in the table, and it is less expensive than the original cost. These are references. Thank you.